Thank you for the introduction. The topic is about building glitch-resistant firmware. As you can see, what we are trying to see is what countermeasures we can have in software for the hardware glitch attacks. So, before we start, just a brief introduction about myself. So, I work at Siemens Technology. Basically, I do hardware security and cloud security. I was associated with, India government's cyber security firm, NCIPC. Then I was at Indian Space Research Organization doing secure embedded systems there. So, and I have a co-speaker with me.
Hello, I'm Chinmay. I'm a master's student at IIIT Bangalore. I'm actually pretty new to security, and this is my first security conference. And my first experience of security was interning at Siemens, and that explains my association with Siemens. I'm mostly an electronics guy. That's what my background is. I focus on digital VLSI design and accelerators, mainly using ASICs and FPGAs. And I also do a bit of embedded systems, and that's what most of today's talk is. And my co-speaker will give you an introduction about the topic, and I'll come back later, hopefully.
Thank you. So I just wanted to know how many of you here know about hardware security. Okay. So, before we, as the title said, software countermeasures for hardware glitch attacks. Maybe I will first introduce, for the benefit of all, what are the hardware glitch attacks, and then slowly, we can go into the countermeasures part. So, what are glitch attacks? So, basically you manipulate the hardware behavior, to bypass something, to bypass some security measures, or to bypass authentication. So instead of, talking about bugs and vulnerability in software, so this is about the physical nature of the hardware. So you try to meddle with the voltage, the clock, all those things. So examples, as I told, you can vary the voltage, or you can meddle with the clock, and there are other advanced glitching attacks like the optical injection, and then you do with the EM, electromagnetic EMI fault injections. So, but what we will be going in depth would be about the voltage glitching, because this is something which is at least can be done a bit easily compared to other advanced optical and EMI attacks. So, what happens in hardware, this voltage glitch, is you have to apply glitch briefly, long enough to induce but short enough not to damage the device or reset it. And you also have to be precise, because that is the also harder part of the glitching. The timing needs to be precise, and it's not that easy that you can do voltage glitching. Sometimes you have to modify the components in a way, like maybe remove the decoupling capacitors or something like that. So if I can show you this plot. So this is something known as SHMO SCUMO plot, they call. So what happens is you have on one side voltage and the frequency. So this plot basically tells you the green region is the safe region for the device to operate. And this red is not good for your device. It might damage or reset it. So if you see, there is a yellow region here. So this is where the glitching happens. So this is the interesting part of the device operating region, where if you glitch it, the device might not be reset or get damaged. You might get the intended behavior you want by either skipping the instructions, something like that. So this is the region where the glitches are basically interested in. So yeah, if you see this, so you have, let's say, 3.2 volt IC or a device. So glitch is something you maybe drop it to 0.8 and not more than that, and something of this range we are talking of. Then what happens to the processor when it want to execute some instruction? So yeah, the most used controller in embedded systems is the Cortex M4. So to understand better what happens when you apply glitch, better we see at the pipeline of it. So you have a clock here, and then basically you would see instruction fetch, instruction decode, and instruction execution. Maybe I'll zoom you for you. Yeah. So maybe you might apply a glitch here or here. So sometimes it's not sure which part of the instruction pipeline is getting corrupted. So either it can be your instruction itself is not fetched, or it was not properly decoded, or while executing the instruction, let's say you have to read the registers, and either you skip the instruction or while reading in the memory bus, the contents of it might be corrupted. So instead of having some 0 value, you might get 1, or 0 0 instead of 1 1 1. So something like that. Yeah, so this is the pipeline of Cortex M4. So I just want to show you that when we say glitch, so any part of this instruction pipeline might be affected, starting from the instruction fetch to the end of writing the contents back into the memory. So that's the thing that the small study which we have done, we would not be sure that which part of the instruction we have corrupted. It's only that either you glitch successfully or not. We cannot pinpoint that, okay, this particular glitch has affected this stage of the instruction. So that is something, it's difficult to pinpoint. So what have we done? We used a fault injector kit. So what does fault injectors do? Right? So this is target. Target, we have used this STM32 chipset, and then you have a fault injector. So you get a trigger from here. So fault injector needs to know when should I start the glitch, right? For that, target should, some hint should go from here to this fault injector to start the trigger, and then it will give us the fault. So this is how usually the fault injector kits would be. You connect it to the PC, you run the code, and your firmware will be running on this target. So basically it makes job of testing easier with this fault injector. Otherwise you need to meddle with the devices. I will show you. We just glitched one basic Arduino. Even that, you need to meddle with its electronics to do it. But if you want to do a study and you want to glitch many times successfully, then you should use something known as this fault injector kits, and we have used this chip whisperer light. I think many of you who know hardware security might know this chip whisperer's light kit. So yeah, we use this chip whisperer light with the STM32F3 target. So this was our fault injector kit which we used, and then this is how the setup would look like. So this is the fault injector, and this is your target board. And if you want to apply it to external, let's say you do not want to use the target provided by the chip whisperer, you might use something external, and then you will be using only the fault injector one. So this is how. Yeah. So let's say the famous Arduino board, if you take, and this is the fault injector, and then you need to give it some connections, and then it will glitch. So, okay, we are glitching, but what do glitches do to the code? So if we take a very simple any C code, the original code, A is code, B is something intermediate which we are not showing, C is the assembly code. So here is where we need to talk when we are talking of skipping the instruction. We cannot talk here because this is where the processor will be executing. So when you say the glitch is able to skip the instruction, it is this instruction. It is at the assembly level that you are skipping the instruction. So let's take a simple password bypass thing. So you can do many things with the glitching, like bypassing secure boot. There are many use cases. So we picked, let's say, bypassing password. Let's say you have a simple embedded device and you need password to log in into that. And let's say this is a very simple password check code. I hope you can see the code, or should I zoom a little bit? Yeah. So if what you see, trigger high, trigger low, these are the triggers because it's a kit, testing kit. So the firmware itself sends when to trigger. Otherwise, you need external trigger from the board. So for testing, yeah, the target itself sends, oh, glitch now. So what happens is, this is the major conditional branch where the password is being compared. You will see the password is shown there, the actual password is touch, and then it's comparing whether the inputted password is same or not. Let's say you glitch here, and then basically what you are doing is somehow you stop processor to check the conditional, whether the password is correct or not. So then it will be bypassed. So this is very simple way of showing how do you do a password bypass using glitching. So maybe I'll show you a video of a setup.
This is the normal setup from before, and we just have an external trigger.
So this is the Arduino board you have, and this is the chip whisperer. So basically you see that in breadboard, because we had to remove the IC from the board because decoupling capacitors would create issue in glitching it properly. So that's why you see the IC on the breadboard. And then you have a code here which checks the password thing, And this is the, so basically we also we should give an indication to the injector kit when should you trigger it. So just before the start of critical section of password authentication check, we would give a trigger, and then you would see that basically glitch, you need to do so many attempts and then you will be succeed. So you'll see, invalid password, and then finally you will see one attempt is succeed, you will see logged in. So this is how basic, password bypass you can do using the glitching thing. So from here, yeah, so now countermeasures. Okay, now you can bypass this password checks using glitching. Now what can you do to prevent this? Okay, there are two methods you can do in the hardware way or also in the software way. So before speaking about the software countermeasures, let's talk about the hardware way. So you can basically have brownout detection circuitry, or you can have some clock and power integrity checks, or you can have some shadow registers or hardware based pointer authentication. So these are some of the hardware countermeasures that you can include in your controllers to mitigate the glitch attacks. But we'll see why it's not the ideal way or not the most economic way to do that. And when it comes to software, so there are some known methods, redundant computation. So instead of checking the password once, you check twice. So the glitch might have, skipped the first check, but your code will execute the second check and it won't give access to the attacker. So this is redundant computation. Second is timing randomization. So the glitch works on, predictable timings. If you randomize when that critical section of the code will run, then it will make a lot harder for the glitch to be successful. And then there is control flow integrity, which means basically for every block you check if the variable is correct. If you see some instruction have been skipped, then you will stall the operation. So basically you are checking the integrity of the flow of the processor. And then with similar logic, you have runtime integrity checks. So these are in brief, different countermeasures. So whatever work we have done is mostly falls under the redundant computation part, and some other the way you write the code also matters. So coming to hardware methods, you have long redesign lead times. If you want to change the hardware of your device, it's not that easy that you can, as easy as you can patch the software. And there is a cost factor involved. So also so this might work. Let's say you want to bring a new product into the market, then you might consider all these things in the design. Let's say there is already product out in the market. So that's not an easy thing that you can do hardware modification in those products. So post deployment you cannot do. So these are some things you cannot do with the hardware methods to counter the glitch attacks. So that's why the study we choose, we wanted to focus on the software countermeasures. The way you write the code matters. So my co-speaker Chinmay will take over and explain you the work we have done, what changes have we done, and how it had impacted the glitch success rate. Over to you, Chinmay.
Thank you so much. So just to give you just to give you a recap, we have, let's say, a password check running on an embedded system. It could be anything. It could be your laptop. It could be your phones or anything. And what voltage glitches aim you to do is, I can glitch that embedded system and I can bypass the password because of the inherent way the default password checker is written. Now, what software countermeasures would mean is what changes can I make to that base code to make sure that the glitch affects the code in a lesser way. So just coming back to the simple password check. So, as you can see, as my co-speaker had mentioned, our aim is to skip this instruction, and this trigger high and trigger low triggers the glitch. So in between trigger high and trigger low, the glitcher would induce multiple glitches to make sure that we can at least skip some of the instructions to make sure we can bypass the password checker. Here, this is the conventional way a password authenticator is written. So essentially it compares each of the, it's a 5-digit password, so the for loop runs for 5 iterations. It's a very simple C code. And over here, if I skip the last iteration of the loop, so when CNT is equal to 4, and I somehow manipulate that iteration to set pass OK equal to 1 with a hardware glitch, I'm into the system. So what better ways can I write this code to make sure it is little less prone to the glitches? And this is on an ongoing effort to make glitch-resistant firmware, and that was the idea of this talk. So, as you can see, we ran this through our glitcher, and out of the attempts, we were able to, we attempted it thrice, and you can see glitch successes of 82, 65, and 74. And that's a pretty big deal. So an attacker only needs to, in fact, get in once, and he can do anything with your system after he's logged in. So let's see what small, simple changes we can make to the code to make sure that it's a little less prone to these glitch attacks. The first thing we decided to do was, notice the loop counter here. The loop counter CNT variable previously was an integer, and now we just changed one word, which is making the integer CNT variable volatile. So essentially what volatile does is it makes sure your compiler, in this case it's C, so a GCC version of the C compiler, it makes sure that the compiler does not optimize your code and leaves it in the raw format. So just by adding this keyword, as you can see, the glitch success rates in our tests show that there's a significant drop, and it's almost like 1, 0, and 0, and previously it was like 80, 60, and 50. So let's try to understand or make up an explanation to why this could be true. So, as I mentioned earlier, volatile versus non-volatile. So non-volatile, and these are the after compiled assembly instructions of both. So the non-volatile one does compiler optimizations. And what do we mean by compiler optimizations? So in a for loop, we need to keep iterating over the loops and making sure that we get the data as fast as possible. That's what compiler optimization is. So when we have non-volatile instructions, notice we have move instructions, and we directly load from registers. Whereas in the volatile, we have load instructions, which means we are loading from main memory. So what this does is, when we load from main memory, it's typically slower and more randomized in terms of timing compared to move, because this is essentially just the data is already in a register, preloaded in a register, and I'm just copying it into another register and using it in the loop. But now I have to actually go to the main memory, for example the RAM, and get instructions, so get the data. So in this case, it'll include complexities like bus interconnects, and it has to, the timing of getting the instructions is randomized when I use volatile. And that is a possible explanation to why this could be working. Now, moving on to something more we tried. There we just changed one word, which is volatile. Now, we mentioned a lot about redundancy. So we have the critical section of code, And what is a glitch attack? A glitch attack essentially tries to manipulate instructions written. So why not add a lot of clutter around the critical section of code? So this is the critical section of code. Why not add a lot more things around it to make sure that the probability of getting your glitch exactly right reduces? So here we tried out duplication. So we have a password stored in the system. We duplicate that password into another variable. And now, if there's a glitch, there's a high possibility that one of these variables, like let's say I'm loading an instruction, there's a high possibility that one of these variables gets corrupted. So let's say the value of the password was touch. Now, when my glitch attack is induced, that touch can probably be turned into apple, God knows. So if one of these variables get manipulated and we run a string compare later when the glitch is triggered, we know that there's a glitch. And if there's a glitch, we will not let you even let you enter the password checker critical section. And even this tremendously reduces the success rate of our glitch attacks. Like even this shows like 1, 0 and 0. So it's much lesser than the simple password checker. So again, just recapping, why did that happen? We duplicated the password, we run a string compare, and the extra verification of the string compare adds extra complexity, which makes it less glitch resistant, which makes it more glitch resistant. So the corruption triggers early and the string compare fails, and we don't even let you check the password critical section code. So in the same sense, we tried similar methods. So instead of duplicating, now we tried inversion of variables. So instead of duplication, so previously we were just copying the value of password into PW1. Now we are inverting and storing it. So we're just essentially trying to add clutter around the code to increase redundancy, to make sure the probability that the glitcher skips the exact instruction is so low that it's almost glitch resistant. And this works in a similar fashion. Right. So 0 glitches across all the 3 attempts. And the explanation is on the similar lines, that inverted password, the password is inverted, and so because we have so much clutter, we almost need perfect timing to exactly skip the instruction we have in the critical section code, and therefore increasing the complexity of getting the glitch right. So thirdly, we also go for masking of variables. Again, pretty similar to duplication. Instead of just duplicating it, we probably multiply the password with a constant 5. And we again do that here to get the value back. And if there's anything corrupted due to the glitch, we don't let you log in. And that's, again, so the results show that it's very glitch resistant. So such simple changes sometimes can make your code very glitch resistant. But let me show you a case where things could go terribly wrong. Yeah, just why did that happen? So just masking does the same thing as duplication, and yeah. So let's show you a case. So look here, glitch successes like 2,700, 2,300, 2,400. So this somehow tremendously made it easier for the attacker to glitch into the system. So this was somehow simply done by just negating the way we are writing the password glitch. So previously we were checking if password was not equal to and setting the password key flag to 0. And here all we are doing is just inverting the logic and checking if the password characters are actually correct and setting the password key flag to 1. So and in the else case, if more often than not, you, as an attacker, you don't know the password, so you would be going into the else case, and we set the password key to 0 and we break. So interestingly, because of this break statement, I just have to, as an attacker, I would be going into the else case because I don't know the password. And if somehow I time my glitch to corrupt the password key variable, and just one bit flip can change my password key of 0 to password key as 1, And if pass OK is 1, that basically folds the system into telling that you are into this, you have entered the correct password. And that is a possible explanation to why just simply negating the logic of the way you write the password glitch code, password authentication code could, cause a lot of issues and make it either much harder or much easier for the attacker to get into the system. So yeah, the way you write code in fact does matter. So why did that previous thing happen? So it was just a single fault was enough to bypass the check because we had the break. And so the lack of strong failure handling and early termination exploit because of the break statement. So let's just show you a compilation of all the methods we tried out. So as you can see, all tests were ran for the same time. So time was constant. So we normalized all the glitch attacks. And, so let's just show you some of the results we have. So, negation was the one I just previously showed you. Negation of the logic. So that was very easy for the attacker to get in. The attacker was able to do a glitch attack on an embedded system and without knowing the password, was able to get in 7,172 times in 10 minutes. And that is a very big deal. And that is negating the logic. And even the simple password checker, the conventional thing written in most places, was breached 221 times. So without knowing the password, I was able to get into the system with a glitch attack 221 times. And the methods we tried, which worked, in fact. There's volatile, duplication, inversion, and masking. And almost all of these methods show significant improvement in the way, in the reduction to the number of entries given to the attacker. So that's what, these methods, probably are the best practices of writing a password checking code, and these work best. Now just moving on to some final conclusions of what can be done.
Thanks, Chinmay. So if we see what are we doing in the real world with the software glitch defenses, so is it not any more academic? There is a very interesting library provided by ARM's trusted firmware project, which is fault injection FIH library. So these are all just will get you started. These libraries will provide you some examples how can you make changes in your code. So this is, I think, a good start. And there is also some open source tools like Glitch Resistor, and there is also the Chip Armor library by this Chip Whisperer guys, New AE guys. So all these open source tools you can have a look at and see how do you make your critical section of the code more secure to the glitches. So I just took the recent announcement, like Wolfboot has advertised its so Wolfboot is Wolf SSL's bootloader. So basically they advertise that their bootloader is glitch resistant. So what does that mean? So you can their code is open, you can go and see. They also added some few of the software countermeasures in their Wolfboot critical section part. People are taking this thing seriously, and they are trying to see what they can try to do with the software countermeasures part, and they are advertising it to on their products that their product is now more glitch resistant. So and then lastly, key takeaways. Basically what we try to tell you is faults are physical, but mitigations can also be logical, which means software way. You don't need to do much. Minimal code tweaks, can be give you big gains there. And then third, try to see if you can use those libraries and get started on that, so that you can make your critical section of the code more secure. So this was the main key takeaways I just wanted audience to have on this. So that's end Will end our presentation? Yeah, happy to answer any few questions. Yeah.
Any questions?
This wolf boot and a secure boot both are the same or the different thing?
Wolf boot is their product name. The secure bootloader's product name is Wolf.
So basically they are also using secure boot, basically which we can see in other software like UEFI, boot and all those things. This is the same thing?
Yeah, it's a bootloader. It's a basic bootloader.
Okay. And this have you heard about ACT2 chip or TAM, Trusted Anchor Module?
Yeah.
So are they going to use in this kind of setups, because the TAM and ACT2 are using in the server domains and all, which are the very costlier one, and they are be used in the data centers. So same kind of stuff are we using in this small motherboard, small setups which will be used in the maybe mobile or somewhere, because your Siemens chip would be required for, I think, small devices, not the bigger one. So how you are maintaining firmware integrity or hardware integrity apart from what you have mentioned there? Anything else is there?
So most of them are using this secure enclaves. They call in ARM's famous trusted zone is also used. So basically those things what they are trying to do is they want to separate the privileged code execution and they are isolating so that the privilege escalation does not happen from your normal user task to the privileged or the critical section. So basically that is those secure enclaves will isolate the privilege escalation part, but very few vendors and there are very few chips out there which specifically provides hardware mitigations for fault injection. So this is a different way. What you're talking is more secure enclaves in trusted zone, trusted execution, where their goal is to prevent the privilege escalation from normal tasks to the critical sections, critical code executions.
You mentioned one of the protection to overcome these kind of issues is to have secure coding, right? Secure coding. So is there some CWE is there when you are is there any possibility to detect by these kind of issues by static code analysis or something like that?
I am not aware of CWE, but I know of an open source project which they looked at the most vulnerable code which might be impacted by fault injections, but it's not a commercial or well-known thing. It's just a small GitHub repo. Maybe I can forward you that. So they does static analysis and they tell, this your code is vulnerable to fault injection. Yeah. SonarQube does not look at from the perspective of fault injection. So they are mostly so insecure coding, so your code is secure to a software hacker, but insecure to a hardware hacker.
Hi, thank you for the amazing talk. I had a question, you mentioned about redundancy in the code, right? But in the scenarios where you have multiple glitches happening on the embedded device, you can even bypass redundancy. So have you thought about, developing these firmwares and whatever you're trying to make on the software side of things from the perspective of multiple faults happening on the device?
So if you see the chip whisperer light which we used, from trigger high to trigger, maybe we'll show the slide. Yeah, from trigger high to trigger low, usually it does multiple glitches. So, and we see it still, it provides that mitigation.
No, so I think from trigger high to trigger low, it does one glitch per cycle. What I mean is, let's say
it does you can define how many glitches it can do. Usually it's around 5-10 is what supported by the chip whisperer thing. That's
Yeah,
what their documentation tells how many glitches they do from trigger high to trigger low.
Okay. Yeah, so I think probably to what I can recall, I think redundancy can be broken by multiple glitch scenario.
Still, if you, these are shorter tests, I would say.
Yeah.
If you do long enough, you might, if you do the multiple glitches precisely, yes, redundancy will be vulnerable to precise multi-glitch. That is there. But getting multi-glitch precisely is,
that's
there was, I think, study done which showed the success, getting a precise multi-glitch is like 10 to 20 times harder than a single glitch.
Yeah, for sure. Yeah, I think it was amazing. I think probably you can do the same thing as Riscure does. They have the rhyme challenge, if you know about it. They have a Arduino Nano. They make these challenges, and then it's for the open source community to break. So probably you guys can put up these challenges or whatever you are trying to make as software countermeasure on GitHub, and then ask the open source people to try to bypass it. I think that would be an amazing activity to do, something as a suggestion from my side.
Thank you for it.
Thank you for that.
Yeah.
Thank you.
Hi. Thank you for the amazing, lecture. But the question that I'm going to ask you is from a business standpoint and not from a technical standpoint. Let's consider a hypothetical scenario where there's a popular firmware product, and let's assume that there is a glitch there, and you have taken the software countermeasure route. Now, the problem is maybe you made the code too complex because of the countermeasures, and now the existing hardware is not able to adequately support it. So in that case, from a business standpoint, as a consultant, what would you suggest the company to do? Like, would you ask them to upgrade the existing hardware where there would be an investment in time and cost? Or would you ask them to continue with the software even though you know that the current hardware would support it for a short period of time, but may eventually become obsolete?
I think when do you apply software and hardware countermeasures? I think you need both in a long term, but let's say the risk is low. It does not make sense from business point of view to invest a lot in secure hardware. So for them it's easier, and also for brownfield projects where you cannot upgrade the existing hardware, I think software countermeasures would work. But in long term, if you want to make your devices secure for, let's say, next few years, and then I think you should consider hardware countermeasures at design stage. So I think one of the point you also mentioned is making code more complex. It won't, because the critical section of the code will be hardly 1% or even less than that. So there you are just adding some redundancy, and that won't increase any overhead or computation time. So you're not losing anything by adding few countermeasures, that too around critical section of the code, which is like less than 1% of your whole code base.
Thank you, Arshid and Chinmay. Please give them a huge round of applause.